Imagine colossal structures, taller than the Eiffel Tower, rising from the ocean's depths. These engineering marvels, known as oil rigs, are among the most impressive feats of human ingenuity, standing over 380 meters tall and weighing millions of tons. From the frigid waters of the North Sea to the challenging conditions of the deepest oceans, installing these massive platforms requires precision, advanced technology, and relentless determination. Capable of producing hundreds of thousands of barrels of oil each day, these rigs represent the backbone of the global energy supply. But what goes into the construction and placement of these giants at sea? And how do engineers overcome the extreme challenges of the ocean environment to keep them operational? We start our journey with the Perdido Spar platform, located in the deep waters of the Gulf of Mexico. Launched in 2010, Perdido was designed to tap into the vast reserves beneath the sea floor, making it one of the deepest oil and gas projects ever undertaken. Situated approximately 320 kilometers south of Texas, Perdido operates at incredible water depths of around 2,450 meters, serving as a production hub for several deepwater fields. With a capacity to process 100,000 barrels of oil and 5.66 million cubic meters of gas per day, the platform, which cost around $4 billion US, has revolutionized the way oil and gas are extracted from such extreme depths. The construction of this colossal platform began with the assembly of its spar hull, a 170-meter-long, 22,000-ton cylindrical structure that was towed from Finland to its destination in the Gulf. Once it arrived, the spar was carefully moored with 9 taut-leg mooring systems, ensuring its stability in waters prone to powerful storms. Its 3 topside structures, housing oil and gas processing units, living quarters, and a drilling rig, were installed later. The platform also manages 35 subsea wells, with both direct vertical access and remote wells, making it a hub of deepwater production. The challenges of constructing Perdido were immense. The sheer depth, combined with the complexity of managing subsea wells, required innovative solutions. Subsea boosting and separation systems were introduced, allowing the oil and gas to be partially processed on the seabed before being pumped to the surface. Furthermore, the installation of pipelines, which stretch over vast distances to transport the extracted resources to shore, required the use of cutting-edge robotics technology. After navigating the depths of the Gulf of Mexico, our next journey takes us to the frigid waters off Russia's Pacific coast, where the Berkut platform stands as a symbol of resilience and engineering mastery. Positioned in the treacherous Sea of Okhotsk, this massive structure was built to endure some of the harshest conditions on the planet, including extreme cold and thick, crushing ice. As part of the larger Sakhalin-1 project, Berkut, which cost about $12 billion US and was estimated to add $9 billion US to Russia's federal budget over the following decade, is not only a critical component for Russia's energy supply, but also the largest oil platform ever constructed in the country, setting a new standard for offshore production. At the heart of Berkut is a gravity-based structure, GBS, fixed firmly to the seabed at a depth of 35 meters. The platform's towering structure, which rises to a height of 144 meters, is equipped with advanced drilling rigs, processing facilities, and living quarters to house its crew. Weighing over 200,000 tons, the platform's size and strength are a testament to the scale of the project, designed to handle the extreme environment it operates in. The platform is capable of withstanding not only freezing temperatures as low as -44 degrees Celsius, but also massive waves reaching 18 meters and the immense pressure of ice up to 2 meters thick. Constructing Berkut was an immense feat of engineering, with parts of the platform being assembled in various locations across the globe before being transported to its final destination. Over 4,000 workers were involved in its construction, with more than 52,000 cubic meters of concrete and 27,000 tons of steel rebar used to build its solid foundation. The platform's topside, weighing 42,000 tons, was carefully installed onto the GBS using cutting-edge technology, including friction pendulum bearings that allow the structure to withstand earthquakes up to a magnitude of 9.0. However, the Berkut project was not without its challenges. The icy seas, unpredictable weather, and logistical difficulties of assembling such a massive structure in remote locations pushed the limits of human ingenuity. The platform's design had to account for the immense pressures of Arctic conditions, ensuring stability and safety for its crew and equipment. As we leave the frozen seas of Russia behind, our next stop takes us to the waters off Norway, where another engineering marvel awaits. Rising from the depths of the North Sea is Troll A, the tallest structure ever moved by mankind. Located about 80 kilometers off Norway's coast, this colossal platform is an integral part of the Troll Field, one of the largest natural gas reserves in the world. Its construction, completed in 1995 at a cost of 4.15 billion Norwegian krone, or approximately $650 million at the time, was a monumental feat, hailed as one of the most ambitious engineering projects ever undertaken. Standing at a staggering 472 meters high, with 303 meters submerged beneath the sea, Troll A is a floating city. Weighing 683,600 tons, this gravity-based structure, GBS, was designed to withstand the harshest conditions of the Norwegian Sea. Built from reinforced concrete and steel, its legs, over 1 meter thick, were constructed using a continuous flow of concrete, ensuring they could endure the intense pressures of the deep waters. The slip-forming process, which poured concrete in a seamless, unbroken fashion, took months to complete, with each 5-centimeter layer requiring 20 minutes to set. This slow, deliberate method was essential for ensuring the strength and durability of the structure. The platform's construction began in 1991, with its base and deck built separately. Once completed, the towering structure was towed 200 kilometers from its construction site in Vats to its final position in the North Sea. The towing operation, which took 7 days, was a carefully orchestrated event that captivated Norway, showcasing the sheer size and scale of Troll A as it moved into place. The platform stands on a solid foundation of concrete, using its immense weight and the force of gravity to anchor itself firmly to the seabed. Despite the success of Troll A's installation, the challenges were immense. The depth of the water, coupled with the pressures at such depths, meant that every stage of construction had to be meticulously planned and executed. Weather conditions in the North Sea added to the complexity, requiring precise timing to ensure the structure remained stable throughout its journey. From the towering heights of Norway's Troll A platform, we now journey to the vast waters off the coast of Australia, where another engineering giant makes its mark. The Prelude FLNG, floating in the Browns Basin, is not only an impressive sight, but the world's largest floating liquefied natural gas (FLNG) facility. This $14 billion project represents a groundbreaking leap in offshore gas production, designed to tap into remote and previously untapped gas fields. Stretching 488 meters in length and 74 meters in width, Prelude FLNG is an enormous double-hulled steel structure weighing an astonishing 600,000 tons when fully loaded. The platform can produce up to 110,000 barrels of oil equivalent per day. Beneath the surface, it sits moored at a depth of 250 meters, held steady by 4 groups of mooring chains attached to suction piles on the seabed. The facility processes gas from the Prelude and Concerto fields, both estimated to hold 3 trillion cubic feet of hydrocarbon reserves. The Prelude FLNG is not only immense, its technological design is equally remarkable. The platform houses 3 LNG processing trains that cool the natural gas to minus 162 degrees Celsius, reducing its volume by 600 times for efficient storage and transportation. The facility's 7 offshore marine loading arms make it possible to directly load LNG, LPG, and condensates onto tankers for global shipping. With 14 subsea risers and 6 umbilicals connecting it to the seabed, Prelude is a sophisticated floating processing plant designed to handle the extreme conditions of the Australian waters, including Category 5 cyclones. One of the most significant challenges faced during the construction of the Prelude FLNG was its size and remote location. Built in South Korea, it had to be towed thousands of kilometers to its final position, where it was carefully moored for what is expected to be a 25-year operational life. The facility's construction required over 260,000 tons of steel and involved more than 5,000 workers globally, showcasing the sheer scale and complexity of this endeavor. As we delve deeper into the realm of colossal offshore platforms, we turn our focus to another remarkable feat of engineering, Hebron, a massive oil platform located in the Jeanne d'Arc Basin off the coast of Newfoundland and Labrador, Canada. This monumental project was not only a technical marvel, but also a significant financial investment, with an estimated cost between $4.85 billion and $5.2 billion. Positioned approximately 340 kilometers southeast of St. John's, this oil platform is designed to withstand some of the harshest conditions on Earth. The Hebron platform is anchored by a gravity-based structure, GBS, a reinforced concrete foundation specially engineered to endure the relentless North Atlantic elements. This includes not only extreme weather, such as waves reaching heights of over 20 meters, but also the threat of icebergs. The GBS is towering 120 meters tall and 130 meters in diameter, providing a stable base for the platform's operation while storing up to 1.2 million barrels of crude oil. With a total weight of 750,000 tons, this behemoth structure supports integrated topsides that include drilling, processing, and utility facilities, as well as living quarters for the crew. The construction process of Hebron's GBS began at the Bull Arm site in Newfoundland. After an elaborate dry dock setup, which included building a bund wall to create a dry construction area, the structure was painstakingly built using 132,000 cubic meters of concrete. Once the base slab was completed, the dry dock was flooded, and the GBS was floated out to a deep-water construction site for further assembly. At this stage, the GBS remained afloat, held in place by 9 mooring lines, as the remaining portions were built. The topsides, towering approximately 110 meters above water, were meticulously fabricated in multiple locations before being integrated at Bull Arm. The final mating of the topsides to the GBS was a critical step, completed while the GBS was still floating. Once connected, the entire structure was towed to its final location offshore. There, it was carefully positioned on the seabed, where it continues to operate as a fully functional oil production platform, capable of supporting production for more than 30 years. Despite its robust design, the Hebron platform faced numerous challenges during its development. The need to ensure stability in iceberg-laden waters, manage the complexities of underwater construction, and provide storage for over 1 million barrels of oil required innovative engineering solutions. These efforts resulted in one of the most impressive offshore structures ever built. As we continue to explore the engineering marvels of the North Sea, our focus shifts to the Gjøa field, located in the northern part of this critical oil and gas region. Situated approximately 50 kilometers northeast of the Troll field, this offshore site was first discovered in 1989. With water depths reaching 360 meters, Gjøa represents one of the most significant developments in Norway's North Sea sector. The field is home to both oil and gas reserves, with estimated holdings of 82 million barrels of oil and 40 billion cubic meters of gas. The total cost of developing this complex project is estimated at 29.3 billion Norwegian krone. To maximize production from the Gjøa field, a semi-submersible floating production facility was designed and deployed. This cutting-edge platform, standing tall in the middle of the North Sea, is equipped to handle the challenging environmental conditions that define the region. The platform's deck measures 110 meters long and 85 meters wide, supported by a hull weighing approximately 15,000 tons. The top side of the platform, which houses processing facilities and operational quarters, adds an additional 22,000 tons, making the structure both formidable and complex. A key feature of the platform is its connection to shore-based power, provided by a 100-kilometer-long subsea cable. This innovation helps reduce carbon emissions by nearly 250,000 metric tons annually, demonstrating a strong commitment to environmental responsibility. The Gjøa field is developed using 5 subsea templates, each with 4 production slots. These subsea structures are strategically located across the field's various segments, tapping into reserves of both oil and gas. The production system was carefully designed to optimize recovery from the field's sandstone reserves, which date back to the Jurassic period. These reservoirs lie at depths of around 2,200 meters and represent a unique set of challenges due to their varied quality and complex fault structures. Over the years, the field has evolved to implement gas blowdown techniques, allowing the gas cap to be produced after initial oil extraction. Additionally, low-pressure production was introduced in 2017 to further enhance recovery. Oil and gas produced from Gjøa are transported through an intricate pipeline network. Stabilized oil is sent through a pipeline connected to the Troll Oil Pipeline 2, which delivers it to the Mongstad terminal for further processing. Meanwhile, rich gas is exported via a 130-kilometer pipeline that connects to the UK's Flags system, with final processing taking place at the St. Fergus terminal in Scotland. These transportation routes ensure that Gjøa's production is efficiently distributed across Europe, contributing significantly to the region's energy supply. Built with advanced technology and meticulous planning, the Gjøa platform represents one of the first floating production facilities to be powered from shore, significantly reducing operational costs and environmental impact. This innovation not only minimizes noise and energy consumption, but also opens the door for further tie-ins with nearby fields, such as Vega and Duva, adding to Gjøa's production capacity. Although production has started to decline, the operators are focused on optimizing output and exploring new opportunities within the field. This includes gas lift techniques, additional drilling, and near-field exploration. With a planned production life until 2025 and the potential for even longer operations through further tie-ins, the Gjøa field remains a critical part of the North Sea's oil and gas landscape. Shifting our focus to the Gjøa oil field, located in the southeastern region of the Norwegian sector of the North Sea, it has experienced a complex journey from discovery to production. Originally brought online in 1996, this field was a significant asset for Norway's oil industry before being shut down in 2001 due to low oil prices. Spanning across 2 main structures, Gamma and Beta, the field's reservoirs hold a mix of oil and gas that made it an attractive target for redevelopment in later years, with costs rising to approximately $1.42 billion. The redevelopment of Gjøa required the installation of modern infrastructure, including a new wellhead module and a jackup rig equipped for both drilling and production. These updates were essential for tapping into the remaining reserves, estimated to be over 60 million barrels. The field's original subsea infrastructure, including a caisson and storage tank, was reused to optimize the redevelopment process, minimizing the need for entirely new facilities. One of the key challenges of the Gjøa field has been its low reservoir pressure, which necessitates artificial lift methods to maintain production. A strategy combining water alternating gas, WAG, injection, and partial water injection was implemented to enhance recovery rates. Additionally, gas produced during operations is re-injected to maintain pressure, while the crude oil is transported using shuttle tankers. The Gjøa field's return to production in 2021, after years of setbacks and redevelopment, marks a major milestone. It serves as an example of how modern technology and engineering solutions can breathe new life into previously abandoned fields. Situated in the northern waters of the North Sea, the Gullfaks oil and gas field has played a significant role in Norway's offshore production landscape. Discovered in 1978, the field is located in Block 3410, where water depths range from 130 to 220 meters. With its initial recoverable reserves estimated at over 2 billion barrels of oil, Gullfaks has been a cornerstone of production in the region for decades. What makes Gullfaks stand out, however, is not only its size, but the infrastructure supporting its operations, a testament to cutting-edge offshore engineering. The development of Gullfaks is anchored by three major production platforms: Gullfaks A, B, and C, which were installed between 1986 and 1989. These platforms sit atop massive concrete structures designed to withstand the harsh conditions of the North Sea. Among them, Gullfaks C stands out for its remarkable engineering feat. The structure reaches a height of 380 meters from the seabed, making it taller than the Eiffel Tower, and it holds the record for the heaviest object ever moved, with a total displacement of between 1.4 and 1.5 million tons. The platforms are critical not only for oil extraction but also for processing, storage, and export operations. The reservoirs in the Gullfaks field consist of Jurassic and Triassic sandstone formations, including the Statfjord Group and Brent Group. These reservoirs, located at depths of 1,700 to 2,000 meters beneath the seabed, contain both oil and gas. The production process involves a complex system where oil is transferred to shuttle tankers via loading buoys, while the gas is sent through pipelines to processing facilities onshore. Gullfaks infrastructure has been continually upgraded over the years to accommodate new technologies and improve recovery rates. In addition to the main platforms, several satellite fields, Gullfaks South, Rimfax, Skinfax, and Gullveg, are tied back to the Gullfaks platforms for production. These satellite fields have been developed with subsea production systems, allowing for efficient extraction and transport of oil and gas. Gullfaks A and C platforms control the operations of these satellite fields remotely, ensuring seamless integration into the broader production system. To optimize recovery from the Gullfaks field, advanced drilling techniques such as horizontal and extended reach wells have been employed. These techniques allow the platforms to access distant sections of the reservoirs, enhancing the field's overall output. In addition, water alternating gas, WAG, injection is used to maintain reservoir pressure and improve oil recovery. This technique involves injecting water and gas in alternating cycles to maximize extraction efficiency while reducing the likelihood of reservoir depletion. Gullfaks has also integrated innovative subsea systems into its production infrastructure. The subsea templates, designed in collaboration with specialized technology companies, allow for the connection of multiple wells to the surface platforms. These templates are equipped with advanced monitoring systems, including multi-phase meters that track the flow of oil, gas, and water. The subsea production system was designed to minimize the need for diver intervention, relying instead on remote-operated vehicles and sophisticated underwater tie-in systems to connect flow lines to the main platforms. One of the key technical advancements in the Gullfaks project is the use of heated flow line bundles. These bundles, which transport well streams from Gullfaks south to the main platforms, are equipped with a system that uses waste heat from the platform's gas turbines to warm the flow lines. This prevents the formation of hydrates and wax, which can clog pipelines, especially during shutdowns. This system not only enhances the efficiency of oil transport, but also provides an environmental benefit by reducing the need for chemical inhibitors. Located in the Jeanne d'Arc Basin, 315 kilometers off the coast of Newfoundland and Labrador, the Hibernia oil and gas field has been a cornerstone of offshore production since its discovery in 1979. But at a cost of nearly $6 billion, this field is home to two major reservoirs, Hibernia and Avalon, which lie at depths of 3,700 meters and 2,400 meters, respectively. It has been a significant source of light, sweet crude oil with low sulfur content, and its initial recoverable reserves were estimated at around 1.2 billion barrels. To ensure the efficient and long-term extraction of these resources, the field was developed with an innovative gravity-based structure, GBS, designed to withstand extreme conditions. The massive GBS was engineered to resist collisions with icebergs, a critical consideration in this harsh environment. This robust design includes a concrete caisson that supports the topsides while housing storage tanks capable of holding 1.3 million barrels of oil. The GBS is further reinforced with an ice wall built from high-strength concrete, which adds another layer of protection against potential iceberg impacts. The platform's topsides are a marvel of engineering, with a design capacity to process 150,000 barrels of oil per day. These topsides consist of multiple supermodules, including facilities for wellheads, processing, utilities, and accommodation for the crew. The components for the topsides were sourced globally and then assembled at the field's deepwater site. The topsides were mated to the submerged GBS, forming the complete production platform. To facilitate the export of oil, Hibernia employs an offshore loading system. This system includes subsea pipelines and a subsurface buoy, enabling shuttle tankers to transport oil to market efficiently. Since production began in 1997, the Hibernia field has continued to evolve, incorporating advanced drilling techniques and water injection systems to enhance oil recovery and extend the field's operational life. As we conclude our exploration of these monumental feats of engineering, we turn our attention to the Piper Alpha platform, a pivotal chapter in the history of oil production. Rising from the North Sea in the late 1970s, the Piper Alpha platform was located approximately 193 kilometers northeast of Aberdeen, Scotland, and became a crucial component of the UK's offshore oil industry. Designed to extract oil and gas from deep reservoirs beneath the seabed, the platform initially processed crude oil, which was then sent to the coast for refining. Over time, the platform was modified to handle gas production, adding layers of complexity to its operations. The platform was a marvel of offshore engineering, built to withstand the harsh environment of the North Sea. The construction featured multiple interconnected modules, each serving a specific function. These included the drilling module, production facilities, and living quarters for the crew. A robust steel jacket supported the platform, extending deep into the seabed to stabilize the often turbulent waters. As with many offshore structures, safety systems were integrated into the design to manage the flow of oil and gas and prevent hazardous conditions. However, these safety systems, while advanced for their time, were not without their flaws. One of the key technical features of Piper Alpha was its separation of oil and gas processes into distinct areas of the platform. The oil extraction and gas compression systems operated nearby, yet were meant to function independently. The platform's layout prioritized efficiency, with pipelines running between different sections, carrying both crude oil and gas to processing facilities onshore. These pipelines were essential to maintaining the flow of hydrocarbons, but also introduced significant risks, as the combination of high-pressure gas and volatile crude oil posed a constant threat of fire or explosion. The gas compression system was added later in the platform's life, amplifying the complexity of operations. This modification required additional safety measures, particularly around the high-pressure pipelines and equipment. However, the integration of these systems into the original design proved challenging, as the platform was not initially intended for gas production. The result was a structure where safety redundancies were stretched, creating vulnerabilities that were not fully addressed. With its immense size and capacity, Piper Alpha symbolized both the promise and peril of offshore oil production. The platform operated at full capacity for years, playing a vital role in the North Sea's oil industry. Yet, beneath its towering structure, unseen risks and design limitations simmered, awaiting the events that would ultimately lead to one of the industry's most catastrophic disasters. If you enjoyed this video, please like, comment, subscribe, and turn on notifications for more fascinating content.